Entropy estimation. Already we have seen in the last slide, last video. This continuation. This is the condition for that last video for entropy estimation in under image compression. First order estimate of H equal to minus summation over K equal to 0 to 3 P of Rk log of P of Rk equal to 1.81 bits per pixel. What is the redundancy? R equal to L average minus H, where L average equal to 8 bits per pixel. R equal to 6.19 bits per pixel. Estimating entropy. Second order estimate of H. Use relative frequencies of pixel blacks image for corresponding this gray level pair count probability. H equal to 2.52 by 2 equal to 1.25 bits per pixel. Gray level pair count probability 21, 21, 91, 95, 95, 169, 169, 243, 243, 21. Count 8, 4, 4, 4, 8, 4. Probability 1 by 4, 1 by 8, 1 by 8, 1 by 8, 1 by 4, 1 by 8. H equal to 2.5 to 2.5 divided by 2. That is half, equal to 1.25 bits per pixel. Estimating entropy. Estimating entropy under in general differences between first order and higher order entropy estimates indicate the presence of interpixel redundancy, that is need to apply some transformation to deal with it. First order, second order, H equal to minus summation over K equal to 0 to 3 P of Rk log of P of Rk equal to 1.81 bits per pixel. Second order, H equal to 2.5 divided by 2 equal to 1.25 bits per pixel. Central image compression model. For this part encoder, this part decoder, f of xy given to, that is image x and y given to function of xy. Here given to source encoder, that source encoder output compression, no redundancies. Okay. So source encoder output is given to channel encoder. Channel encoder noise tolerant representation. Additional bits are included to guarantee detection and correction of errors due to transmission over the channel. Hamming code. Additional bits are included to guarantee detection and correction of errors due to transmission over the channel. So this encoder output given to channel output given to channel decoder. After this full here decoder, before this channel here encoder, after this channel is the decoder. So here channel output given to channel decoder output given to source decoder output is the f cap of xy. This is the general image compression model. We will focus on the source encoder decoder only. Encoder f of xy equal to f of xy given to mapper. Here mapper outside output no interpixel redundancies, reversible. Here no here the reversible, no interpixel redundancies. So mapper output given to quantizer. Quantizer output given to symbol encoder. Quantizer output is no psychovisual redundancies, not reversible in general. So quantizer output given to symbol encoder. Symbol encoder output given as given to channel. So symbol encoder output is the no coding redundancies reversible. Here no interpixel redundancies reversible. Here no coding redundancies. Here no coding. Here no interpixel redundancies. Mapper transforms data to account for interpixel redundancies. Mapper is the transforms data to account for interpixel redundancies. Quantizer quantizes the data to account for psychovisual redundancies. Symbol encoder encodes the data to account for coding redundancies. Okay. Now we are going to see decoder. Channel output given to symbol decoder. Symbol decoder given to dequantizer. Dequantizer output given to inverse mapper. Inverse mapper output is the our total output, that is compressed output, that is f of x y f cap of xy. The decoder applies the inverse steps. No, here after compressed image, original image will come. Note that quantum is irreversible in general. Compress f of xy given to compress output given as g of xy given to decompress output is the f of x f cap of xy. Last I told you, sorry for that, f cap of xy is the compressed, no, decompressed. Yeah, sorry, I correctly told. Here compress output. Here decompress only. That is original image will come. That's all. Here only compressed image. Here decompressed. Original. That is original output here will come. This is the original. So after the decompression, this is available. So how close is f of xy to f cap xy criteria? Subjective. Based on human observes. Objective. Based on mathematically defined criteria. Subjective fidelity criteria. Rating. Value 1, 2, 3, 4, 5, 6. Rating excellent, fine, possible, marginal, inferior, unusable. Description. For value 1, excellent, an image extremely high quality, as good as you could desire. Value 2, fine, an image of high quality, providing enjoyable viewing. Interference is not objectionable. 3, possible, an image of acceptable quality. Interference is not objectionable. 4th, marginal, an image of poor quality. You wish you could improve it. Interference is somewhat objectionable. In value 5, inferior, a very poor image, but you could watch it. Objectionable. Interference is definitely present. 6th value, rated unusable. An image is so bad that you could not watch it. Objective fidelity criteria. Root mean square error. Short form RMS. We know already. ERMS equal to root of 1 by mn summation over x equal to 0 to m minus 1 and summation over y equal to 0 to n minus 1 f cap of x comma y minus f of xy whole square. This is the root mean square. RMS. root mean square error. Mean square signal to noise ratio. SNR MS equal to summation over x equal to 0 to m minus n, summation over y equal to 0 to n minus 1 int, int f cap of xy x comma y whole square divided by summation over x equal to 0 to m minus 1 summation over y equal to 0 to n minus 1 f cap of xy minus f, f, f of xy of whole square. Lossless compression f of xy compression f of xy given to compression output given to decompression output f cap of xy e of xy equal to f cap of xy minus f of xy equal to 0. This is the lossless compression. In taxonomy of lossless methods, lossless coding techniques, entropy coding, repetitive sequence coding (RLE), run length encoding, statistical encoding, Huffman arithmetic (LZW), lossless predictive coding (TPCM), bit plane encoding. C. Image compression techniques per Huffman coding addresses coding redundancy. A variable length coding technique. Source output, that is gray levels A K. It is encoding. After encoding, compression can be achieved by encoding AK appropriately. Then decode, the same result will come. Encode, decode. Enable the code, disable the code. We can say like this. Okay. So A of K here given available. So compression can be achieved by encoding AK appropriately. At AK, what we are doing here? Compression. Compression can be achieved due to encoding appropriately. So gray levels. Source symbols, that is pixel values, are encoded one at a time. There is 1-to-1 correspondence between source symbols and code words. There is 1-to-1 correspondence between source and symbols. Source symbols and code words. Optimal code minimizes code word length per source symbol. Huffman coding under forward pass sort probabilities per symbol. Combine the lowest two probabilities. Repeat step 2 until only two probabilities remain. Original source, source reduction, symbol A2, A6, A1, A4, A3, A5. Probability 0.4, 0.3, 0.1, 0.1, 0.06, 0.04. 1, 2, 3, 4. Source reduction 6, 4. Save 6, 4, 3. 0.4, 0.3, 0.1, 0.1, say 0.06. Here maximum value, here less value than above. Then 6, 4, 0.06, 0.04. Adding here 1. So this 1 plus 1, here 2. So 4, 3, 0.4, 0.3, 0.2, 0.1. Then add these two. 0.4, 0.3, 0.2 plus 0.1, 0.3. Then we have to add 0.3 plus 0.3 is 0.6, 0.4 here. So sort probabilities per symbol, combine the lowest two probabilities, repeat step 2 until only two probabilities remain. Backward pass assign the codes